Okay. So I think, yeah, so you're going to want to mute me so that my voice is not echoing through your phones. Um, or no, not mute me. That's bad. Mute your phone. Well, yes, sorry. Don't mute me. All right. I'm going to proceed under the assumption that everything is working. Um, cool. Thank you, Pat. All right. So from the top, yeah, let me go back to the very top. All right. Yes, in this paper, I introduce expressivity. In the presentation, I'm going to start by explaining this term by stepping back a little bit. Uh, the study of concept learning seeks to understand how we learn, use, and communicate concepts. But what even is a concept in the first place? At this view from the bridge, we can think of a concept in two forms. So one form is the extension, which is just a list of observed examples. And the other form is an intension, which is a representation that may stand in for those observed examples. Concept learning studies have typically proceeded by presenting a learner with an extension first, measuring behavior in some way, and then using that measurement of behavior to make an inference about the learned intention. There are a variety of means of doing this, too many perhaps to go into now, but one influential recent method is the representation linked hypothesis. This proposal suggests that when people learn concepts, the difficulty of learning that concept is proportional to the complexity of the representation that's learned. So I'll illustrate what this means. Here's a brief illustration of how this works. To the left, we have an extension of concepts, and to the right, we have their definitions in a Boolean-like language. The ordering here comes from a classic result by Bruner, Goodnow, and Austin. This result has since been replicated several times. This also illustrates a second point, which is that the underlying representation used matters. So a very perplexing result in some ways in the early literature is that and concepts are learned more easily than or concepts. Hold on. Sorry. Yes, that and concepts are learned more easily than or concepts. However, this does not fall out itself from the representation linked hypothesis. In order to get that result from this hypothesis, you must also have a representation that prioritizes and operations over or operations. Some exemplar models do this, and many rule-based models do as well. And once this is done, once prioritizing and operations over or is done, then the representation linked hypothesis gets the ordering right. So before moving forward, I want to quickly gloss over what I mean when I talk about expressivity. The ability to express a wider range of concepts is a good thing generally. For one, it allows us to model concepts that are more interesting and ecologically valid than the blue and red circles from the very beginning. This has been a trend in concept learning to move toward models that use more expressive representations, as well as concepts that require more expressive representations. I'll also here plug my work with Pat that showed that concepts that underlie counting and arithmetic cannot be learned without a second order logic. And there's more about what that second order logic looks like in the paper. And also one of the results that we showed, or one of the things that we did was extend teaching models to use first order logic. So the important point here is a somewhat general one, that representation systems matter. In recent years, the representation linked hypothesis has been a common method for assessing different parts of models in the concept learning literature. But I want to really focus in on two recent results, especially as they contact expressivity. So Steve Pianadosi and colleagues found that concepts that require more expressive representations are also learned more easily, or often learned more easily than concepts that do not. So first order logic is a great example. The assumption has typically been that first order logic is more complex, almost categorically, than Boolean logic, for instance. But they found several first order logic concepts that are learned quite easily. Charles Kemp found a model, or built a model that uses first order logic. And he found that that model is often a better predictor of learning than Boolean logic, even for concepts that do not require first order logic. So together, these results suggest that representations, as well as the representation length hypothesis alone, are important, that representation length on its own is probably insufficient for the study of concept learning, and they point to expressivity and the ways that we might consider it. So there are several problems that this leads to. I address many of them in the paper, but here in the presentation, I'm going to focus in on one. This one involves, so much of the work that I've discussed is preoccupied with comparing different models. So according to the representation length hypothesis or measures of expressivity, but it's possible that a single individual concept might have a representation with structure at different levels. So rather than comparing different models for a single concept, there might be concepts that have representations that have structure that uses different representations. So this is related to ideas in the literature, hybrid models of concept learning like Nosofsky and colleagues' rule plus exceptions model. And it's a notable difference from other approaches in the concept learning literature. Rather than competing representations for explaining learning on single concepts, I'm discussing complementary representations within a single concept. So also, I'm going to take a minute here to say, feel free to interrupt me on the YouTube, or if not, just tell somebody to interrupt me at any time, because these ideas are somewhat important they're very important for understanding the experiments that follow. So in the experiments that follow, I will discuss geometric concepts that I believe have structure at both the object level, which roughly corresponds to Boolean expressivity, as well as the relational level, which roughly corresponds to first order logic expressivity. Relational and object level concepts have been studied extensively on their own, but I'm going to be looking at how those different concept structures actually interact. The fact that these two structures have different expressivity is of particular importance here. And the reason is that evidence at one level, at the object level, cannot necessarily rule out all alternative hypotheses at the relational level. This is important for learners because a major assumption in the literature has often been that learners learn by ruling out, or one way that learners might learn is by ruling out alternative hypotheses. To see what I mean, consider the example that subject C. I've taken individual screenshots of the actual training phase in the experiments that I'll talk about later, but just look at the examples that our learners see. At the object level, each of these can roll out alternative definitions for what a rhombus is. So a rhombus is simply a quadrilateral that has all sides parallel and not necessarily all interior angles at 90 degrees. They can rule out all alternative explanations at the object level here. However, at the relational level, the subject can never observe that all of the shapes that are labeled rhombus are also labeled parallelogram. The subject can only ever observe evidence that is consistent with some, but not all rhombuses are also parallelograms, as well as all rhombuses are also parallelograms. So this is a subtle point, but it's key to understanding how expressivity is the difference between these two levels. Okay, I think everybody's still on board. So, okay, so I'm going to go over in the next couple slides the actual concepts that I use in the experiments. Here, I've got the object level definitions of 4 geometric concepts. These are all quadrilaterals. Um, the quadrilaterals differ on 2 dimensions, so they differ on whether or not the interior angles are right angles, and they differ along whether or not all sides are equal. So here in the left-hand corner, I have the actual Boolean logic definition from the paper, but you can definitely understand this in natural language as well. On top of the Boolean level definition, on top of the object level definition, sorry, there's a relational level definition. The relation that is used in this work is the subset relation. So again, the object level evidence doesn't necessarily rule out all alternative concepts at this relational level. However, there are ways that subjects still might get there. For instance, subjects might assume that the 2 features from the previous slide, let me go back. If the subjects assume that these 2 features are the only relevant features, they might infer logically, they would infer logically this subset relation. However, the evidence that they're shown does not suggest that there are no other relevant features. Okay, if everybody is on board, I'm going to move on to explaining the experiments now. Okay, so experiment 1, the aim was to simply demonstrate the dual structure of concepts. Oh, and before I proceed too much further, I should note that all the analyses for experiment 1 specifically are done post hoc, and experiment 1 and 2 are work done in collaboration with Kyle McDonald, Mike Frank, and then Pat as well. So the aim here was simply to demonstrate the dual structure of these concepts, because this is not something that had been demonstrated at all to our knowledge. In order to do this, we have 2 conditions. We have a learning condition where subjects are given optimal examples according to a learning algorithm in order to learn one of the 4 concepts. And then a baseline condition where they're simply just shown the examples that might be labeled but given no true or false feedback about them. So the procedure here, we had a relational level pre and post test, and in between that test, we had the learning condition. So just to illustrate that a little bit more visually for you, yeah, so the design was relational pre and post test. The measure of interest here is the improvement on the relational test from pre-test to post-test. Yeah, and again, for the learning conditions, you can see here that subjects were told which shape they were learning, and they were given 3, and they actually clicked on the 3 shapes one by one, and were told either it was true if it's blue or false if it's red. The baseline condition was shown exactly this image here, but none of them were labeled, so there was no label feedback. So the main results here, the difference score is what I'm calling the difference between the post-test and pre-test recall. Here, the baseline and teaching scores were similar. This is the main comparison that I was interested in. However, and also different scores for the aggregate group are different from 0. So there does appear to be an effect of seeing these the relational test twice, but there doesn't appear to be an added effect of the learning condition. So here's the different scores broken up by question. So here are the 12 questions. Most of them are not significantly different from 0. There's one that may be, but this is post hoc, so it's hard to say exactly. Okay, so experiment 1 indicated that perhaps learning at the object level does not lead to learning at the relational level. But this is a difficult thing to know exactly without actually measuring learning at the object level in order to compare it with the relational level. So for experiment 2, I replaced the training phase with a design that allows us to actually measure that learning at the object level. This design was within subjects. Participants were again recruited through Mechanical Turk. So the actual training sequence, what it looked like is there are 16 unique example label pairs. So we have the shape that is strictly a square, and then the label that's a square. We have 4 different shapes, 4 different labels, so you get 16 total pairs. they were shown all of these in randomized order, and they were asked to label each of them yes or no. I'll move to this next slide. So this is it's this in the middle. So they were shown a shape, asked if it was a rhombus, and then yes or no, and they were given feedback after each one. So the criterion was if they correctly labeled all 16 example label pairs for 2 consecutive trials. So this was a fairly strict criterion. They were given 15 total trials, and what I did was use the results from experiment 1 as a baseline for what we would expect if there was no learning at the object level. So here are the results for the learning rate. So this is how the subjects learned across trial. Sorry. Yes, this is the average rate of error for subjects grouped by the number of trials remaining. I also divided them by whether or not they reached criterion. Those who did not are in red here, and then those who did are in black. So critically, both groups actually showed significant progress as the trials went on. So the slopes of the regression for each group is non-zero. Yes, and 13 out of 39 subjects reached criterion. That gave us our 2 groups. So here the difference score for those that actually reach criterion is greater than those from experiment 1. However, the aggregate group, if you consider that both of them actually learned at the object level, the aggregate group did not differ from experiment 1. Even though these subjects were exposed to similar material for a much longer time, given much more feedback. So this suggests that another analysis, actually comparing the learning at the object level to the relational level, is appropriate. If what is happening is an actual transfer of learning from the object level to the relational level, we should expect the amount that a subject improves at the object level to predict the amount that the subject improves at the relational level. And this hypothesis critically does not depend on separating subjects according to whether or not they reach criterion. So object level improvement here for either group or together does not predict relational level improvement. So here's a summary of the 2 experiments that have been run that I do have data for. So it seems that learning at the object level does not promote learning at the relational level when we use somewhat common rational learning methods. However, when we separate subjects out according to our criterion, we do see weak improvement. However, that improvement does not result in the improvement at the object level actually being able to predict the improvement at the relational level. It's simply that the final score for the group that reached criterion is higher than the final score for the baseline group. Sorry. So this leads to experiment 3, where I'm trying to test a learning procedure that should at least have a good shot at promoting transfer of learning from the object level to the relational level. So the idea is that we can order examples according to a representation, and both Matthew and Feldman, as well as Baxter Eves and Pat Shafto, have shown that by using such an order that respects the underlying representation, one can promote learning of that representation. The application that I have here, though, is critically different because we're showing examples that apply at one level, the object level, while ordering them at the relational level. So I'll show you what that looks like in a second. But before leaving this slide, yeah, we're going to have enough participants according to as good of a power analysis as we had the data for in each a shape order, a label order, and a random order condition. The amount of time in the payment was good for the experiment 2, so I'm going to keep that. So here's what this looks like. The shape order, as you can see, orders them by shape. There are different visual representations of each shape, so this may not look like it's exactly the same, but each of these is strictly a rhombus, meaning that it is a rhombus and not a square. It also happens to be a parallelogram. And so we ask them about each of those. Actually, sorry, each of these is a strictly parallelogram. It's not a rhombus or a rectangle or a square. So yeah, for the shape order, we keep that. I'm going to keep that constant while asking each of the 4 different labels. And for the label order, I will do the exact converse with labels. So keep the label constant and alternate randomly the shapes. And this will be compared to a random order condition where, where it's going to be just like experiment 2, where the actual shapes and the labels both are randomized. So I have 2 proposed analyses here. The first is that either the shape or label order or both are expected to show greater relational level improvement than the random condition or the baseline. So this is simply because, as I said, these orders should respect the representation of the relational level, and if that's true, then yeah, we should get better learning, even though the examples are coming in at the object level. Additionally, and this is perhaps even the stronger test. In these cases, if what is happening is an actual like transfer of learning from the object level to relational level, then we should find that in those 2 conditions where the examples are ordered according to the underlying representation, we should find a correlation that the object level improvement should predict the relational level improvement, while the random order condition should be very similar to experiments 2 and 1. Okay, so I'll wrap up by summarizing some main points. The beginning of the talk simply seeks to make the point that expressivity is important. So there's this pre-existing trend toward more expressive models that has maybe not been as explicitly acknowledged as would be helpful. But on top of that, using expressivity, it's able to complement existing methods. So not only should we care about whether or not the representation length of a representation predicts learning difficulty, but we should care about whether the model is able to express concepts that require more expressive languages. So on top of this, I've shown preliminary work that indicates that some important concepts actually have structure at multiple levels of expressivity. So not only do they have structure that use different representations, but those different representations seem to have different levels of expressivity because the most basic learning methods, or the most common learning methods rather, do not promote learning at both levels. So yeah, and that's the final main result, is that these learning methods that have been tried in several experiments, they do apply well at the object level. This is a simple replication in that case, but the transfer to the higher levels of expressivity seems questionable at best. Okay, so that is that's the talk. I'm assuming everybody can still hear me. Should I call in? Okay, so I'm going to address John's question. Hold on. Is this working now? Yes. So John's question is, how about another example of object level versus relational level learning? Extremely good question. So this current example that we have is sort of like science. It's serendipitous. And I thought that they had a separation and other people didn't. And the results seemed to show that they actually have expressivity. In general, anything that has something like a for all statement or a there exists statement should require a first order logic level of expressivity. And that's because there's several examples. I believe like this is maybe the root of the black swan example, where if you see swans of one color, that does not actually imply the next one is not going to be of like the color that you've never seen. So I think that like something like that is a great example of a concept that actually has structure at different levels. An interesting one that had like structure that seemed important and non-trivial at both levels was difficult. I don't actually have another example, though I would be interested to try. Is that a sufficient answer? Is there if you have any follow-up questions, feel free. Yes, so that's another very good question. So let me go to this slide. So I believe you're talking specifically about the correlation here, Nick. That's okay. So I'll address Nick's and then I'll go to John's follow-up. So yeah, I believe Nick is talking about the correlational question. What happens if they're flat or relatively flat? So it would not surprise me that if here the shape and label order were a little bit lower, but maybe slightly higher than random and possibly not different, little or no correlation. In that case, I think this is still a very interesting result because it implies that there's this other structure that almost all of the concept learning ignored, that concept learning literature used to teach it do not work at both levels. So I think I can think of other follow-ups. I'm not sure how related they are, but I think it will still be a very interesting result, and there will still be a lot of directions to go from there. Yeah, so I mentioned, a couple taxonomic relations with John's question. And I don't think the dual structure should be limited to that, but since concepts in taxonomy, this is like common from like Rush and Mervis's work, where it's just like since they have like a clear structured definition, you can talk about different levels. My levels are a little bit different from the ones that they talked about, but without taxonomies, it becomes a little bit more difficult to pin down at least real examples. Yes, I absolutely agree. And I think this one, either way that this comes out, it should absolutely provide like a meaningful result. Yeah, I think the idea that like I've tried just about every trick in the book that I know of for teaching object level concepts, and if the finding is that none of those tricks actually work to teach the relational level concepts, that is quite a significant result. Okay, so going on to Marcy's question. Yeah, the reason is so the simple answer is just for completeness. There's there's reasons just to think that subjects might learn at the object level better in these conditions because it requires like fewer things to keep in working memory. Like on the nth trial, you've seen fewer either labels or shapes or both. Um, and what I'm really interested in is exactly like in what way respecting the relational representation would allow or promote a transfer of learning from the object level. So both of them actually respect that in different ways. Since the subject relation, or yes, since the subset relation has two inputs, it has like all rhombuses are also parallelograms. Then both sides of that actually matter, and it's an interesting question about which of those matters more, or if they both matter equally. And I don't have the data or the background work to actually um, make me feel strongly about either one. So that's why I'm including both. All right, really good questions, by the way. I'm sorry again about the technical difficulties, um, but thanks for sticking with it, everybody. All right, yeah. So Keith's question is about attention checks. So I typically don't. And the reason is I think they can cut both ways with Amazon Mechanical Turk. So on this one, we have some free response about like what the task was, exactly like what they learned in it. Um, but I wouldn't want to, so especially in this one, because we're already separating those that reach criterion from those that didn't in one of our conditions. I think it might be unfair as far as the results go to eliminate people who might answer poorly on like a final sort of question and have like essentially a second criterion. Um, so we might weed out all the people who got the task mostly, but maybe not completely. Um, so I think that's a good thing, and we actually have them in a sense, but we haven't found that weeding people out according to the question like what did you learn has changed the results any. Um, but yeah, I guess there's very little to lose from adding attentional checks. So that's something that I'll consider for the third experiment. I haven't written or run it yet, so. Okay, so Nick asked, what do we learn more broadly if experiment 3 comes out as I expect? What does that mean for a teacher, for example? So yes, this is a very good question. So I think the sort of like takeaway point is that when a concept that we're teaching has structure at multiple levels, we need to consider all of the levels that we want to teach when we are providing examples for that. So if you just teach at the most basic level, you should not expect kids or any student rather to transfer that learning to the more expressive level. I think the maybe not for teachers specifically, but for like the psychological literature, I think it means that we really need to prioritize representations even more than we already appreciate. So if things like subtle aspects of learning, like ordering of examples according to representations, is what matters for learners acquiring the full concept that we desire for them to learn, then we need to know exactly what that representation is, or we need to at least have a really good idea. And without that idea of the representation, um, a method like ordering examples to respect the higher expressivity representation would not work. Okay, so Nix has another question about the difficulty of the task and reaction time data. So yeah, so reaction time data is actually fairly straightforward to collect in Amazon Mechanical Turk. I have not been collecting them. Um, the task, it seems, is pretty difficult, and it's definitely using it on Amazon Mechanical Turk changes the rate at which the subjects pass. So if I remember correctly, this is the in an experiment 2 and experiment 3, the training phase is very similar to like Shepard, Hovland, Jenkins. It's been replicated on Amazon Turk previously by Crump et al. And they found that while the overall results were very similar, the rate of reaching criterion was like much lower. Subjects took longer, and fewer subjects eventually reached that criterion. Um, so I'd be curious to look at reaction time. The representational sort of like hypotheses actually have something to say about reaction time. There are papers that show that like for simpler concepts, people respond more quickly. So so there is room there, and that might be like a future direction to apply these like representational ideas to reaction time as well as accuracy. Okay. So I'll get to Marcy's question first. So wouldn't it work as just as well to provide conceptual instruction first? So that is a great question. There's work that I really like about I think it's from Tom Griffiths' lab, Bushbaum and Griffiths about um, cultural learning, learning across cultural generations. And one of the interesting results that they have is that you need to, they call it posterior passing. But essentially what this is giving the next generation a description of what you know rather than specific examples. And they liken that to passing your posterior odds of your model inside of your head or something. But that's the thing that talking about conceptual instruction brings to mind first, and I think that's a real possibility because yeah, so I'm very sort of conspicuously restricting the information these subjects get to object level information, and what that would look at like at the representational level is literally just telling them that all rhombuses are also rectangles. And this is one of the reasons why I don't call this exactly first order logic, because um, people have done experiments where that first order logic relation is distilled into like a true or false feature, just saying all rhombuses are also parallelograms, and they've taught them as if they're at the object level. So it's possible that that could work, and that's another interesting direction. And I'm not. It's in that case. There's then the question of like, does understanding go the other direction from relational level knowledge to object level knowledge, or if you present examples at both levels, do they interact? Is it harmful or distracting? So, so hopefully I did that justice. If I didn't, please follow up. So I'll go to Nick's. I should touch on the technical things in my final write-up. That is very good advice. Yes. So I'll make an effort to do that. And yes, Keith, my plan, if you mean experiments 1 through 3, I do plan to include all of those in my final dissertation. So going to John's, in the long run, where do I hope this work leads? If I make it to Mecca, where will I be? What will I be doing? Okay, so that's a fun analogy. I think so Pat and I have done a lot of work on specifically teaching, but I tend to think of that work as representational as well, if not even primarily representational. So this was one of the interesting results from one of our big paper is that teaching can actually imply certain representations. But here in my dissertation, and I guess in Mecca, if I ever make it there, um, the the goal will be to just provide a fuller understanding of what the representation used for learning is, if there's a single one, and in the more likely case, like what do they look like? How do they interact? This is this is critical for a number of things, but if we want to like understand, much less automate any part of learning, we actually have to understand the way that like concept representations interact and work. So that's why I think this is interesting, and the results, either way they come out, will be important. So going to Nick's question, would there be value in doing an experiment so Marcy mentioned earlier, providing conceptual instruction first. So my assumption is that that conceptual instruction would I there's a few ways that that could be instantiated. It might actually look like instruction at the relational level. It also might specifically tell learners that they're going to learn things in a simple level, but they're going to be asked to infer how these concepts relate to each other. In either way, I think there would be value in doing that experiment. I'm not sure. So if the question is about like whether I should include that in my dissertation or not, I think that's a judgment call, and that's sort of, yeah, I'm going to not commit to saying either way. I'm definitely interested in that experiment. I think that's a really, really good idea. And I think it does follow on. I'm just not, my concern would be if it was conceptually connected enough to the first 3 experiments, or potentially if the results conflicted, it might be difficult to interpret. So yes, yeah, John's ellipses. Yeah, I would say that most of the work I do is looking for representations. That's a good boiling it down. Oh yes, yes. So for Keith's question, originally we were comparing optimal learning examples, and we were like providing learners with optimal learning examples versus exploration. So active learning versus guided learning in certain ways. Um, this and basically the unfortunate result was that there seemed to be no learning at all. And that was because it was my sort of intuition or suggestion that this was because we were actually testing at one level while training at another level. Um, so that's the background. It was originally meant to just be sort of a straightforward guided versus active learning experiment. So this work is not going to be published. It had only been through an initial analysis in that direction. Um, so yeah, so that's I guess that's the background. I don't know if there are any more questions about that, but I'm happy to go into more detail. Yeah, and I think I really tried to be careful about clearly noting which results were post hoc versus which ones were not. So thanks, Marcy. Okay, yeah, I'll clarify that rationale to Marcy. So the rationale dividing into the two groups for experiment two. Um, so the main hypothesis was that learning at the object level isn't transferred to learning at the relational level. So there were two ways to test that, and I showed both ways. And one way is to just say those that reach the criterion are the ones that learned at the object level, and asking if they learned at the relational level um, more so than those in the first experiment that were essentially shown no training. So the reason I wasn't comfortable leaving it at that, though, it does provide like some rejection of that hypothesis that there's no transfer, but I didn't want to leave it there because there does seem to be learning even in the group that does not reach criterion. And I believe it was Keith that mentioned, either Keith or Nick, somebody mentioned that this seemed to be a somewhat difficult task. Only 13 out of 39 subjects actually reached the criterion. And but like in spite of that, both groups, both the criterion and not criterion group, did seem to have learning as the trials progressed. So because of that, I added the second analysis where they're not separated, where we just look at the improvement at the object level and compare it to the improvement at the relational level. Oh, so Marcy's question, couldn't the ones who reach criterion have just had better pretest and post-test scores? So I did the difference between them. So I just did improvement on the relational level and compared that to improvement on the object level, which is just at the object level, it was from the very first trial to the one either where they reached criterion or ran out of time. And then on the relational one, it was pre versus post. All right, so Keith's question, do I think my experiments will shed light on why transfer is often rare? So, oh, sorry. Am I still there? Okay, yeah, so do I think my experiments will shed light on why transfer is often rare? It's possible. I'm not, I'll be, I think a little bit of humility is deserved because you're right. It's a real concern and it is rare, but I think if potentially experiment 3 turns out the way I expect, it will show at least one way that we might promote transfer, which is a little bit difficult, admittedly. You have to know the underlying representation, you have to know how that relates to the representation at the other level, and you have to organize the examples so that they respect each other. And that's a difficult thing, and that's something that one of the reasons I'm using geometric concepts is because the definitions are so clear in those cases that we can clearly say how the order affects the representation, or how it relates to the representation at the relational level. Um, so so hopefully there will be tentative evidence that we can promote transfer in certain cases. Though I definitely think that there's a lot of work to be done after that about exactly how that's done, even if there is one somewhat clean answer. Okay, and Nick says that this is precisely the sort of thing that I should include in my dissertation, and that is very good advice. Okay, yeah. So Keith, did I appreciate that. I think that's a really good comment. Did I address it enough? Is there a follow-up that you'd like to hear my thoughts on more specifically? Okay.